Now we are moving on to the next stage where we are discretizing the whole equation. Okay, so now for the example we take up this equation, which is an unsteady one-dimensional heat conduction equation, and constant thermal diffusivity is the simplest equation we can think of, only two terms, but you would have noticed that all the equations are much more complicated than this, but still we will use this to show the process that what we are doing. So this is our equation, and now what we are doing is, at first stage, let us replace the first order partial derivative in the above equation with forward difference formulation. So this is our forward difference formulation for this is okay. Now here this is the first derivative of time, of temperature with respect to time. Okay. Now what are these subscripts? We will talk about them. These subscripts have nothing to do with the derivative. Okay, it's not the second derivative, third derivative, or like that. So this is representing the position on x-axis, right? I, j, k, or 1, 2, 3. Rather, instead of I, j, k, it is I1, I2, I3, I4, and so on. Okay, and this is your time step. Time is changing from 0 to 1 to 2 to 3 and so on. So the first we are talking about this equation. This is a unsteady one-dimensional heat conduction equation with constant thermal diffusivity. Constant thermal diffusivity means alpha is constant. Okay. Now what we are doing is that we are writing this equation, this term, we are discretizing this as well as we are discretizing this term. Okay. Now when we discretize this first term, we are doing forward difference method. Okay, and in the forward difference method, this is the truncation error. Then for the second term, we did this central difference method, and this is the truncation error. And simply what we are doing is we are substituting both this expression into the equations. Okay, so this is our original equation and this is our difference equation, along with these are the truncation error. Now what we are doing, as far as so long you are counting the truncation error, your expression is exact. You are having the exact formulation. But then you cannot go along with truncation error, so you drop them, assuming that they are small. And how do you make them small? By making delta t and delta x very small, negligible. So what happens is this becomes your equation. Okay, and this is an algebraic equation which is called difference equation, right? And it represents the partial differential equation. And I said that this is an approximation because we have left out the truncation error, and the order of truncation error is given here. Order is 1 in case of time and twice 2 in case of delta x. Okay. Now a point to be noted, I told you again and again that this is an important point, and that you will understand the value importance of delta t and delta x, that the equation which we are making is approximation, and the error depends upon delta t and delta x. And whatever, if suppose it is a 3D case, it will be delta x, delta y, delta z and delta t, all the 4 coordinates. So you are not talking about the exact equation, you are talking about an approximate equation. Only thing you can approach closer to it by reducing time interval and space interval. Okay. Now then one more thing, this equation which you have written is only at one point of the grid. Okay. Now the similar equation has to be written for all the grid points. So you have okay. So you have to write equation at I plus 1, I minus I plus 2, and so on. And if you are on the other side, you have less than I, so you'll have I minus 1, I minus 2, and so on. On all these points, you have to write the equation. Okay. On the other side, for time, n is equal to 0, 1, 2, 3, and so on. You have to write the this equation for all of them. Okay. Now, then it says that we can only hope that numerical solution of the above equation is the same as obtained by the analytical solution of the original partial differential equation within the limitation of truncation error. Now, the original equations are partial differential equation. Solution of them, and then the approximate equation, there is the algebraic equation or the difference equation, solution of them. There are two different set of problems now. There are two different set of solutions now. We can only hope that the two solutions are matching, because ultimately we are finding the solution. So it's just a hypothesis or just a expectation that these two are matching. They may not match, right? And within the limitation of truncation error. We don't know what will be the effect of truncation error. It can be more or less. We are assuming that to the extent we made the truncation error, the results will be affected only to that extent. Right? But you can't say so. A small error actually may blow up. Right? So first you make a small error, then you are expecting that the final solution will also have a small error, which is a hypothetical. It's not sure. So here we talk about something about how we are sure that our errors are within the limit. Some confidence in this regard can be obtained if we can answer yes to the following question. So there are stages by which you reach to that conclusion. Does the difference equation reduce to the original equation as the number of grid points approach to infinity, that is delta x approaches to 0 and delta t approaches to 0? So first thing we have to check that whether these equations approach each other. Okay. Still, what is happening is that you are converting partial differential equation into algebraic equations. Okay. Truncation error is a infinite number of terms. Right? Now, if delta t approaches to 0 or delta x approaches to 0, what is happening? You have sigma, you can say, infinite terms are there, that is n is equal to 1 to infinity terms are there. Okay, and they are a function of, you can say, a delta t raised to power n and delta xi, or even delta x raised to power m. Okay. Now you know that each of these terms is approaching 0 because delta t is approaching 0, right? And delta x is also approaching. But when you are summing up for the infinite times, will that sum will approach to 0 or not? So we have to check that reduce the original does the difference equation reduce the original differential equation as the number of grid points approach to infinity. So we just have to see that our truncation error approaches to 0. Remember, truncation error is made up of infinite terms. Each of them is very small, right? But that does not mean that you are adding smaller terms infinite number of times will be 0. Okay, you have to see that series actually converges. Okay. Examining equation 14.4, we note that the truncation error approaches to 0, and hence the difference equation does indeed approach to the original differential equation. Now this one has to see, because actually fortunately you have number division. The terms are of the order delta t raised to power n divided by n factorial. Now factorial is such a function which overtakes all other functions. So what happens is that the later terms becomes insignificant, because factorial rises at a very high value rate. So that thing can be seen. Okay. When this is the case, the finite difference representation of the partial differential equation is said to be consistent. Now the first thing, this consistent word is important. Okay. What we are saying is that our finite difference representation of the partial differential equation. So finite difference equation of the partial differential equation, they are approximately same, and this is consistent if truncation error approaches to 0. Okay, so this is called consistency, one term. Okay, so what is consistent? When truncation error reduces to 0 as space and time interval approaches 0, the algebraic equivalent to a partial differential equation is termed as consistent formulation. So we can say our formulation is consistent. Okay, and the condition for that is our truncation error should approach to 0. Okay. If the difference equation is consistent, then there is still an issue. The issue is that numerical algorithm used to solve the difference equation is stable. Now you are going to solve it by iteration. What does the stable means? That your solution, whatever formulation you have made, you can say the algorithm you have made to solve those equations, they do not blow up. They follow a normal process. Okay, because you are going to do it again and again and again. So the numerical algorithm should be stable. It's something like that. Sometimes when it happens that division by 0, log of 0, something like that, some certain terms like comes there, and which is what is called that in mathematics there is a term for that a point is created where you cannot define, undefined function हो जाता है. ठीक है, तो वो जो है एल्गोरिदम आपका फेल हो जाएगा वहाँ पे. और इट कैन फेल बाय अदर मेथड ऑल्सो. कोई लूप में फंस जाए. what टाइप ऑफ आपने प्रोग्रामिंग किया होगा. इफ़ यू आर डिवाइडिंग बाय 0 your computer will hack, or you are end up in a loop where it is repeating. You're still not able to come out. or it has gone into a track where unpredictable answers are coming. It's quite possible. Okay. Now, and if the boundary conditions are handled in a proper numerical fashion, then the numerical solution of the difference equation should be an appropriate representation of the analytical solution of the partial differential, at least within the truncation error. So it is saying that three things are required. One is that your difference equation should be consistent, your numerical algorithm should be stable, and your boundary conditions have been properly taken care of. Okay, so I would say that boundary conditions is part of that only when you are writing the equation. So that means you have written consistent equation for boundary condition also, right? So these are the three conditions. However, there are several big ifs in the above system. These ifs, along with undesirable propagation of truncation error throughout the domain, make any successful CFD solution somewhat a challenge and sometimes an art more than a science, right? So what you are basically doing, as far as finite difference equation, writing that, till that point it is okay. Now when you want to find out the solution of that, you have to ensure that your truncation error approach to zero, the methodology which you are using is stable algorithm, and your boundary conditions are properly taken care of. Okay, so all these are the ifs, and you have to ensure them. And one, he is talking about undesirable propagation of the truncation error. It is quite possible that your truncation error is adding up. There is a difference here. Truncation error in one particular step and the effect of truncation error at the end. Consistency means truncation error in step 1, that whatever equation you have, differential equation and your difference equation, they are nearly equal in the acceptable zone. That is your truncation error problem at level 1, where truncation error is actually very small and all the errors do not add up, all the terms do not add up and make it blow up. So your truncation error is small. But now this is a propagation of truncation error. Second is propagation of truncation error. What is it? That because you are going in steps, so each time truncation error is going to come, and if it is going to add up each time, is going to create a problem, because truncation error should be sometime positive, sometime negative, and then they will keep on cancelling each other. Their effect should be such that it is positive or negative. So it's basically, if you have this is the actual path of your solution, you are actually moving like this, near about. Sometimes you go left, sometimes you go right, sometimes you go left, sometimes you go right. So you are not very off from the result. But if each time your error is on the same side, you are going to go much away from your solution. Okay. Now then we talk about stability. Now this is about the propagation of truncation. If a given numerical error is amplified in going on from one step to the next, then the calculation will become unstable. Right? Numerical error is not amplified. That is the stability. If the error does not grow, especially if it decreases from one step to another, it is solution is said to be stable. Okay. Now we talk about discretization error. It's just a way of describing what are the errors. So discretization error is simply truncation error for the difference equation plus any error introduced by numerical treatment of the boundary condition. Okay. So there are two types of error. One is a discretization error. Discretization error is because you have converted partial differential equation to finite difference equation. Okay? There will be plus truncation error. And this also includes your boundary conditions. So the error is because you have discretized the equation. So this is a discretization error. Okay? Then there is a round off error. Another error which is coming now. Now round off error is the numerical error introduced after a repeated number of calculations in which the computer is constantly rounding the numbers to some significant figure. That is a round off. Because your computers are finite computers, they are limited. You cannot go to the infinite decimal, and forget about infinite decimal, you cannot go beyond 10, 15 or something like that. Right? That means you are leaving out, every time you are leaving out something. But that should not add on the same side all the time. Okay? So that is called round off error. At each step you are making a round off error. Okay? So let us put them in a different form. First is that A is your analytical solution of partial differential equation. So you have a partial differential equation, you find the solution to it, and the solution is A, and that is a perfect solution. No approximation you have made. You have partial differential equations, you have the solution to it. Okay. The second is you have made partial differential equation into difference equation. You have discretized them, and you can find the solution to them. That is the solution is exact solution. So all these algebraic equation you are writing, they are exact solution. So on one side you have partial differential equations, on one side you have finite difference equations. Okay? This gives you analytical solution, this gives you exact solutions. But these two solutions will be different because the equations are different. Okay. So now when you are solving this, you cannot solve them exactly, you make approximation. Why? Because there are lot many number of equations. If there were only 3 or 4 equations, you could have solved them. Maybe 10, 15 you could have used computer and done it. We are talking in terms of millions of equations. And they have to be solved. They are all algebraic equations. They all have the exact solution, but you cannot solve. Even with computer you cannot solve. So you are doing some approximation in the computer itself. Right? So that is the numerical solution of this. So you have a numerical solution here. So one error occurred here and one error occurred here. There are two types of error which are occurring. One is because of discretization, one is because of the solution of the discretized equation cannot be done directly. It has to be done through approximate methods. Okay. Now, so the discretization error is called A minus D. The difference between the exact solution, analytical solution, and the exact solution of the finite difference equation. Here the error is because your equations have changed. And here the second error is, the first error, this is your epsilon 1, I may say. This is because your equations have changed, right? And this is your second error. In the process I have written only epsilon 1. Second error, because you are not able to find the exact solution, you are using approximate method to find the solution, right? Now there is an analogy, or you can say there is a, we will drop this for the time being, because this requires some more exercise before we reach this point. Okay. Actually what we do, we solve these equation and try to show that the subsequent error, that means epsilon, you can say n plus 1 divided by epsilon 1 n, this will be less than or equal to 1. Now if your error each time is reducing, then you can say your solution is stable. तो ये उसका analysis है, but we will, and this is called von Neumann stability method. So the method which you are adopting, you have to be sure that it will be stable. Okay. Now we talk about this explicit formulation and implicit formulations. Okay. It's a simple. Only thing we should know what does explicit and implicit means. Now what we would do, we will see from the example itself. We have this equation, okay, and we have finite difference form like this. Up to this point we have already done, okay. Now this equation can be written like this. Now what we are doing is, there is only one term here which is n plus 1. On the right side all the terms are of n. This is n plus 1. So if you see this equation, on the left side it is n plus 1, on the right side it is n. Now n plus 1 is the forward step, this next step, time step next. So if you know the solution at n step, right side is known to you. So each next step solution depends upon the previous step. It is called a marching solution. And this is an explicit formulation because all the terms on the right side are known. I have told you about what is a explicit formulation and implicit formulation. I can just tell you again here. So I write x is equal to, or 3x is equal to 5p and 2y is equal to 20. Right? Now p is known to me, p is, let us say, 100. This is explicit formulation. Here x can be found out and y can be found out independently. When these equations are independent, they are explicit. Suppose I write an equation like this: 3x plus 2y is equal to 5 and 3x minus 3y is equal to 0. Now this equation cannot be solved individually. This is called implicit, right? Even if I write it as 3x is equal to 5 minus 2y, I cannot solve this. If I write this equation as 3x is equal to 3y, I cannot solve it, because on the right side there is a term which I don't know. This is implicit, and this is your explicit, right? So So this is the difference. So if you look at this equation, this is an explicit formulation, right? This is called, it is a parabolic partial differential equation. There is a name for this. It's called parabolic equation. Okay? Now we can see it from here on the grid graph. This is, suppose T is the temperature, this is your x-axis, right? This is your time step, right? And T is the unknown temperature. Now what happens is, if you want to find out temperature at any of these points, right? So you will find in terms of these points. So what is happening is, these values are known. From there you find this value. Once these are known, you find these values. This is called time marching. You are moving from one step to another to another. So at every time, at a particular time, you know all the temperatures, and you can keep on moving ahead. This is called a parabolic solution, parabolic equations, or time marching. The special name is given to it, time marching. You are marching in time, right? Now, if you look at the equation, you will find that this is your T3, and suppose I say it is n equal to 1, n equal to 2, this will be T3, 2. Now, this is a function of what? T2, 1, T3, 1, T4, 1. So what it is showing, the temperature at this point depends on these 3 points. This is how your equation is. You can look at this equation. On the left side is this, n plus 1, Ti n plus 1. And on the right side, you will have Ti minus 1, n, comma Ti n, comma Ti plus 1 n. These. So you can say this point is dependent on this, right? So this is also an explicit formulation. It is like this. These term you will get from the equation itself. You can look at this. 2 time step n plus 1 at point 2 is in terms of point 2, 3, 2 and 1 at time step n. Explicit. So this is one formulation. By definition, in an explicit approach, each difference equation contains only one unknown. So there is only one unknown here, and therefore can be solved explicitly for this unknown in a straightforward manner. You can do it simply, there is no problem. Nothing could be simpler than this. अगर यही solution तरीका होता तो CFD would have been very simple. What is the problem? Okay. Now you may say in this graph that when you talk about this point, right? So there is no point here, right? But this is actually a boundary point. So boundary points are already defined at all the points, at all the time. So that is not a problem. Okay. Now there is a approach which is called Crank-Nicholson approach form. Now this formulation which we gave you, explicit formulation, has some problems. So Crank-Nicholson is a person who improved upon this, and a small change he made. He only said that each term will be a sum of the forward and the backward, forward and the current. So here what you are finding, the equation is changed. These are the two terms on the left side. On the right side, all the terms were n. He said no. What I will do, I'll take temperature at that point and temperature at that point in the next step and divide them by 2. So this is n plus 1, n divided by 2, n plus 1, n divided by 2, n plus 1. Now what does that do? This makes this equation implicit. And now this equation cannot be solved on its own. But still it is very popular because of its stability. Okay. So this is called Crank-Nicholson form. It's a very popular form, and that is why I picked it up. You should be remembering this. In CFD, Crank-Nicholson form or its modified versions are used frequently for finite difference solution of boundary layer equation. When you are talking about boundary layer, this is very well used. But otherwise also it can be used. This is an example of implicit approach. Okay. By definition, the implicit approach is one where unknowns must be obtained simultaneous solution, where the unknowns must be obtained by simultaneous solution of the difference equation. What we have done, on the right side we already knew the values from the previous step. Now we made it current step and the previous step. So the current is not known, so you are stuck up. Okay. Now implicit methods involve large matrix operation. In explicit formulation, all equations are independent. You can solve them independently. In implicit formulation, all of them have to be solved together. That means you have to do matrix solution, and it makes it lot more complicated. But then why we are using it? There is a benefit of it. That is why we are. Otherwise, that would have remained in theory and we would not have talked about it. कि कभी किसी ने ऐसा try किया था, ठीक है? But it's no use. Leave it. Right? तो ये जो चीज़ है, अब इसमें क्या है कि explicit का advantage क्या है? Relatively simple to set up the and program. इसका प्रोग्रामिंग बहुत सिंपल है, ठीक है. डिसएडवांटेज क्या है? वाई डू वी नॉट टेक एक्सप्लिसिट? इन द अबव एक्सप्लिसिट फॉर्मुलेशन इक्वेशन नंबर दिस, द टाइम स्टेप मस्ट बी लेस देन ए लिमिट इम्पोज बाय स्टेबिलिटी कंस्ट्रेंट. इफ यू वांट योर इक्वेशन सॉल्यूशन टू बी स्टेबल, द टाइम स्टेप्स शुड बी स्मॉल. देयर इज ए लिमिट ऑन दैट, विद इन ए लिमिट, एंड दैट इज सो स्मॉल. Now what will happen? If your time step is small, then you will have to do more number of time steps for the same calculation. Okay. In some cases, the limit may be very small, which would result in a long computer time to solve the problem for a given interval of time. Now, even when it is an explicit approach, because you want the solution to be stable, solution procedure to be stable, you have to reduce the time steps so much that the calculation in the explicit mode will come out to be taking more time than the implicit approach. Are you getting the point? While solving each step is very quick in explicit, but then the number of steps increases so much that it becomes uneconomical from the calculation point of view. Okay. Now, implicit approach formulation, stability can be maintained over a much large values of time interval. For stability consideration, you can have a large time step. Hence, using considerably fewer time steps to make calculation over a given interval of time. So, you want to calculate the problem, solve the problem for a given amount of time. Now, the number of time steps will be reduced. Okay. This may result in less computed time. Okay. Now, what is the disadvantage? Disadvantage is that the computer program to solve implicit formulation is complicated. Now, you will have to solve the whole matrix. Programming will become difficult. The computer time per time step is much larger than the time in the explicit approach. Now, for each time step, implicit approach is very costly, but the number of time steps required are less. And that is how it becomes cheaper. Since a large time step can be taken, the truncation error becomes large. Now, because your time step is large, your truncation error will also be large. However, for a time dependent solution which is a steady state is desired, time wise accuracy is not. Now, suppose you only want steady state solution, intermediate solution is not required. So, intermediate accuracy is also not required. Are you getting the point? It's like this. You start from here. Okay. This is your end point. Okay. Now, one way is you are approaching your solution like this. I should rather use another ink. You are following this path, you are going this. Okay. The second approach is that you go like this. The second approach, what it has done, it has actually remained all along the real solution throughout the time. But it took a lot of time. In the second approach, what happened? That it was deviating very much. So it was making shortcuts. Finally, both of them reach at the same point. And if you are bothered only about the final solution, there is no need where. So if somebody is taking shortcuts, some hopping here and there, and reaching the correct point, and another person is actually following the exact route and reaching the same point. So if you are concerned only with the reaching the same point, it doesn't make a difference how much you have deviated on the way. Implicit approach would, because delta t is more. It will be making much errors on the way, but finally it will reach the real point solution. So, this is the end of it. Hence, an implicit approach with a larger time step may be adopted. So, I'll just sum up what we did. One is that we had started from the point where we had partial differential terms which we discretize, and we had number of ways of that. Forward difference. For the first derivative we have three methods: forward difference, backward difference, and central difference. Similarly, for the second derivative we have one method, that was central difference. Then for the mixed derivative we had the central difference method. Okay, and that was a simple, because there could be other one derivatives also, and you can find other schemes also. Then we did for boundary points. in the boundary points we had a problem that we cannot go on the backward side, we had to take forward point, and there we took 2 forward points to improve the accuracy of the, instead of going for 1 forward point, we took 2 forward points and saw that our formulation was accurate. That was as far as the individual terms are concerned. Then we moved on to the equations. When we talk about equations, then we do the individual terms, discretize them, and you get a truncation error, combined truncation error, and a finite difference equation. Now, so we have a finite difference equation. Now, so you have original equation is partial differential equation. You can find the solution for that hypothetically, let us say, we call it A. We discretize it to get a finite difference equation and find its exact solution, call it D. Right? And because we cannot find D, because it's a very lengthy process, we go for approximation. So instead of finding the exact solution of finite difference equation, we find the approximate solution of finite difference equation, that is called N. So there are 2 errors which we commit, and they are called discretization error. Discretization error and round off error. The first error was discretization error, because we moved continuous equation, differential equation to finite difference equation. Then the second error was because we, in our algorithm there was an error, round off error was there, okay, and other approximation will also be there. So you get a round off error. Now then our objective is so that this error does not blow up. That is called the stability. We try to reduce that. We have not discussed much about it. Only thing that they are important. Then we talked about 2 different types of formulation, implicit and explicit. Explicit, we know that on the right side all the terms are known, that is explicit, and time marching problem, they are called parabolic differential equations. If you solve them, it's not always, your equation may not be always parabolic, they can be hyperbolic, they can be elliptical. Okay, so this is a parabolic equations where you move from one step to another and you can find the solution of the next step based on the previous step. That is your marching solution. But explicit formulation, we find that sometimes it takes more time, it is unstable, you go modify it, and one of the modification is that is of Crank-Nicholson method. What we are doing is on the right side, whatever terms are there for the current step, we take them as average of the current, original we have of the previous step, now we have the term as the average of current and the previous step. So the right side also becomes unknown. That becomes implicit formulation. And that formulation we have to solve by matrix. But what we find is, because we can increase the time step, you have to do less calculation in the implicit form as compared to explicit form. So sometimes you prefer implicit form. And then we have talked about that, especially if you are talking about the steady state solution, it does not matter how much you deviate on the way. Implicit form, because they have delta t more, they will deviate. Their truncation error will be more. So they will be making more error on the way, but finally they reach the same point. Okay. And in the explicit form, you are following the path solution all along the. So you are accurate all throughout the time. It depends which one you want. Okay. So this is what all about.